What's up, guys? Okay, so we did the first few questions of this in class. In case you weren't there, if you want to check answers or whatever, here's the answers to number 1, looking at a velocity time graph. Here's all the answers for quiz 8.2. We were just doing setups of areas and mostly areas, all in 8.2. All right, and then 8.3, we were doing setups of areas and volumes and average value, okay? And we talked about extra problem A with no calculator, and we were just kind of in the middle of this calculator question, all right? Okay, so just to like confirm what we were doing here. So I was letting y1 equal ln of x, that's the one on the top. y2 equaling x minus 2, that's the line on the bottom. And then a and b, I was able to find those intersection points. And I stored them in a and b, and I wrote over here what I wanted a to equal and what I wanted b to equal, okay? And so it was just from a to b of y1 minus y2, and I put that in my calculator, all right? Now the solid generated, if we're going down around the line y equals -3, I'm basically, what I'm doing is I'm adding 3 to each of my, integrals. Now, let me see if I still have this equation typed in. I don't know that I do, but let's take a look. Okay. Let's pull up our graphing calculators. Okay, so I've got my equations in there, ln x, x minus 2. Let's see if my a and b were saved. I think it is. Yep, that was a, and that was b. Okay, perfect. So you guys, to find the volume of the solid generated, it was pi integral from a to b, okay? And then it was, now I can just do, instead of retyping ln x, I can go y1 plus 3 squared, all right? And then minus, and then the inner radius, which was, whoops, get back over there. Okay, y2 plus 3 squared. All right, and then this is all as a dx. Okay, and you can even just write that whole thing on your paper for the graders, even using the a and b and the y1 and y2, as long as you state what those all equal. This gives me 34.198. All right, as my volume. All right, you guys, now, what we're going to do is we're going to take this same solid here, but we're actually going to rotate it around the y-axis. Now, this is a totally different thing because now in the middle of the problem, we're actually switching to a dy, okay? So that seems a little bit tricky. We're still rotating it, so it's pi, and then it's outer radius squared, inner radius squared. All right, but we got to figure out what the outer and inner radiuses are, okay? Now, check it out, you guys. So we've talked about how in order to do a dy, we have to solve these equations in terms of x. Okay, if y equals ln of x, okay, and I do e to both sides, x is e to the y. The distance from here to here, okay, so it's no longer y equals ln of x. That distance is e to the y, okay? Now we have this line y equals x minus 2. Well, it's actually x equals y plus 2. And so the distance from here to here is x equals y plus 2. Now, the outer radius is going to be that one, the y plus 2. The inner radius is going to be e to the y. So when I set this up, this is going to be the outer radius minus the inner radius. Okay, now the other thing though that we talked about is we do have to have endpoints here. And you guys, the problem is I don't have my y coordinates. I kind of just wrote that down, A and B, but I don't have my y values, all right? Well, if I go back into my calculator where I was graphing and I'm calculating this intersection point, okay, and let's go ahead and go to this one first because we go bottom to top anyway. Whoops, get back over there. All right, 1, 2, 3, all right. And you guys see it's negative 1.841406. And that's the y value. I can just write down that whole thing. And then if I calculate the intersection on this side, and I need the y value. So if I had noticed before, I maybe would have actually just called the y value, like wrote down the y values as well, 1.1461932. So this is my setup, okay? All right, so I've got from my y to my y, and then I've got the further squared minus the inner squared. Right, but do not evaluate. Okay, perfect, there we go. All right. Okay, cool, so here's an extra problem that we can practice. Okay, now the big thing with something like this, you guys, is you got to be able to sketch it. This is why it's so important to know what like e to the x, e to the 2x, what this stuff looks like, okay? Okay, so check it out. The x-axis, the y-axis, the line x equals 1. Okay, this is the line x equals 1. And then e to the 2x, you guys, well, the point 0, 1. And then the point 1 is at e squared, and e is like a little bit less than 2, so e squared would be a little less than 9. So it'd be like up there. Okay, so, and then the x-axis and the y-axis. So here we go. So I have this little like volume area right here. All right. X equals 1 and e to the 2x. Okay, perfect. And we're revolving this around the x-axis, which is good. That means I can do a dx. All right. So they're going to be pi. It doesn't look like there's an inner and an outer radius. There's just a radius squared as a dx. All right. Okay, now, because the top is, this top equation is e to the 2x. This bottom equation is 0, so I'm actually have to like use 0. So anyway, this is going to be e to the 2x squared. So that's pi radius squared. And it goes from the x value of 0 to the x value of 1, because it told me that it cut off at x equals 1. Now I can actually do this problem pretty easily. E to the 2x squared is e to the 4x. And you guys, when I integrate that, it becomes e to the 4x over 4. I'm going to put the over 4 out front with the pi. Okay? So I'm going to get e to the 4 times 1, e to the 4 times 0. So that's going to be e to the 4th minus 1. So that's my volume right there. Is actually just pi over 4, e to the 4th minus 1. Okay? Okay, here's another great question. This was on 2005, the BC question number 1. For a lot of years, it's not the same now, but every FRQ number 1 on the BC test was an area volume, like for a lot of years. Okay. All right, so I've got f of x, and f of x is this one. Okay, and I've got g of x. G of x is this one. All right, perfect. Let R be the shaded region in the first quadrant enclosed by the y-axis and the graphs of f and g. F be the shaded region enclosed by f and g as shown in the figure, blah, blah, blah. Find the area of R. Cool. This is a calculator question. All right, guys. So step 1, let me go put this into my calculator. Let's just go into the y equals, and we will go. Okay, 1/4. I always like to just do alpha fraction. It's just easier. Plus sine pi x. All right, and then my next equation is 4 to the negative x. I'll start off with just like a zoom 6. All right, and then I'm like, oh yeah, it only wanted this little region in the first quadrant. So why don't I zoom? You could go zoom, you could try zoom in, you could try zoom box. Let me zoom in a little bit. That gives me a great picture. So I need to find this intersection point right here. Let's see, cool. And I need to come right up here and find that point. 2, 3. All right. And let me just see real quick. Horizontal line y equals. Yeah, these are all going to be dx's, okay? So I just had to read through a, b, and c and make sure we weren't switching to a dy, and we're not. So I'm going to go ahead and put this intersect point right here. I'm going to just go ahead and call that a. All right? Excuse me. My goodness. All right. So what I'm going to do is I'm going to come out here, and since I just found it in x, I'm going to let x store alpha a. All right, and I'm going to write that on my paper. Let a equal 0.17821. Hold on, let me write this better. Okay. 0.178218047. And then I'm going to go back into here. I'm going to calculate the intersect point, and I got to do this one over here. 1, 2, 3. And that's, oh, that's a nice intersect point. Okay, and then that one's just at 1. And I could just write 1, so I don't need to say let b equal or whatever. Okay, so if we go back to my picture here, I'm basically going 0 to that a number and 1. All right? Okay, so the area of R is the integral from 0 to a, and since I said let a equal, I don't have to retype that whole thing. All right, so 0 to a. And in R, it's g of x on the top, and it's f of x on the bottom. That's all the graders are looking for on that, right? And then I can literally just go out to the front, and I can go, what is the integral from 0 to a of, and then my g of x was under my y2, I believe. So I go alpha trace y2 minus alpha trace y1, and this is a dx. Okay, so the area of this little teeny tiny thing, all right, is 0.06475. All right, now for this next one, to find the area of S, now it's going to be from a to 1, and this time f of x was on the top, and g of x was on the bottom. And then that's all I have to write for that, because then I can just go over to my calculator, and I can go math 9, and then a up to 1, and then this time I go alpha trace, I go y1, because I want to do my f of x minus alpha trace y2 dx. Okay, and I get 0.41036, blah, blah, blah. Okay, so just go to like 3 decimal places there. All right, perfect. Find the volume of the solid generated when S. Now, we're only talking about S right now, not R. When S is revolved around the horizontal line y equals -1. That's that line right there. All right. Now, I know because I'm rotating a volume, it's going to be pi r squared. And I also know it's going to be outer r minus inner r. It's a dx since I am rotating it this way. That's a dx. Okay, I know my endpoints are a and 1. All right, now this is where this gets a little bit tricky, is setting up for your 2 radiuses. Okay, so measure, remember we're going to S, from here to here. So you guys, from there to there is what f of x is. It's just the y value. It's f of x, and then I'm adding 1 since it's below it. So this is going to be f of x plus 1. Okay, and then for my next part, my inner radius, well, here to here is g of x, and I'm adding 1. So my inner radius is going to be g of x plus 1. And then all I do is I go over to my calculator, okay, and I go pi, and then, no, not a second, math 9, the integral from a to 1 of, okay, so I go parenthesis y1 plus 1 squared minus parenthesis y2 plus 1 squared dx. Okay? And I get 4.558 for my volume for that one. All right, perfect. Okay, so I don't know, you guys, once you can get the setups of these, they're like really not too bad. All right, no calculator. All right, perfect. Okay, the area of the shaded region, great. Oh, it just says f of x, but it doesn't actually tell me what f of x is. Fabulous. So that's going to be the integral from 0 to 5 of f of x. Love that for us. Okay, the volume by revolving around the x-axis. Okay, guys, that's here. All right? So that volume is going to be 0 to 5, and if I'm rotating around, it's pi r squared, and that's f of x. That's the radius. Okay? The volume of the solid formed by the region along the line y equals -2. Okay, that's the line y equals -2. All right. Pi. And then this one is going to have an inner radius squared, outer radius squared. Oh, sorry, it's going 1 to 5. I don't know why I kept putting 0 to 5. It's going 1 to 5. Okay, that one's going 1 to 5. That one's going 1 to 5. All right, you guys, the outer radius, so this line right here is f of x. And then since that's down 2, it's plus 2. So the outer radius is f of x plus 2. The inner radius is literally just that, which is just a 2. Okay, so that's how I would set that one up. All right, the perimeter of the shaded region, this is weird. We haven't talked about this that much, but this is arc length. And for now, if it's on your test, I'm going to just let you like have the formula for it because, shoot, I don't remember what the formula is. But let's see if I can find it. Where did we do arc length? That's washers, discs. Thinking it's like right around here somewhere. Area between two curves. Was it in 8.1? RIP, okay? The integral from a to b of the square root of 1 plus the derivative squared. All right? So I'll just go on here. The integral from 1 to 5. Square root of 1 plus f prime squared dx. Okay, setting all that up. All right, that's pretty good. Let's see if we got all those correct. Good, perfect. Why is this 4 plus? Oh, shoot, dang. Okay, that's pretty smart. Okay, look at this. That integral, you guys, gives me, let's see, the arc length. Does that give me the perimeter of the figure? No, because I still have to add that part to get the whole perimeter, and the base of that is 4. So that's the arc length. So the perimeter will be 4 plus this arc length. Okay? So that's it for this first part of the review. Oh, sorry, allergies. Let's go ahead and look at the second part of the review. Let me pull that up for you guys. Alrighty, guys. Okay, so let's go ahead and look at these problems here. Okay, for problems 1 to 5, use the graph and table at the right. Show an integral setup for average density of hikers between mile 1 and 5. All right, average density is like average value. So I'm going to use 1 over b minus a, the integral from a to b. Okay? So it'll be 1 over, from 1 to 5, 5 minus 1, the integral from 1 to 5 of d of x dx. Cool. Okay. Number 2. Use a midpoint sum with n equals 2 to approximate this value, because it didn't give us like an actual equation that I can integrate. So we're going to use a midpoint sum with n equals 2. So that means that I'm going to go from 1 to 5. So I'll go 1 to 3 will be my first one, my first rectangle, and 3 to 5. Okay. And remember that the height of the rectangles comes from the midpoint on here. All right. So to approximate this area from 1 to 5, so it's going to be, I still have to do 1 over b minus a in the front, okay? This rectangle has a base of 2 and a height of whatever f of 2 is. This rectangle has a base of 2 and a height of whatever f of 4 is. So that's 2 times 35 plus 2 times 25, which is 70 plus 50. So the area is 120, but when I divide by 4, the average density is 30. And then we could say hikers per mile or whatever. So it means like the average of all the hikers is like right around there, between 1 and 5, which kind of makes sense. Okay. Use 4 equal width trapezoids to approximate this average density on the same interval. All right. So now we're going to do trapezoids, but we got to do 4 of them. Okay, and each one is just like that. All right, I'll do this one up here. The average is still 1 over b minus a, and then I have to do a bunch of trapezoids here, okay? Okay, so my first one has a base of 1, and then the heights of each side. Remember, trapezoid, I got to do a half also. 1/2 times 1, and then it's f of 1 plus f of 2. That's the first trapezoid, so you got to add both sides, okay? The second trapezoid is 1/2 1, and then it's f of 2 plus f of 3. Definitely going to need some more room here, okay? F of 2 plus f of 3. The next trapezoid is 1/2 base, and then it's f of 3, f of 4. And then the last one is 1/2 base, and then it's f of 4, f of 5. Okay? So this is like pretty complicated here. Oh, dude, this is an FRQ. I don't have to solve that. Let's go. All right? I don't even have to solve that. Okay? It's just the average value of, and then I just did trapezoids. Nice. Okay. For number 4, this says estimate where the density is equal to the same average density. So, the average density from 2 or from 3? Maybe it's the same. Let me look. I guess maybe I do have to figure this out, which is big bummer. All right, this is going to be 40 plus 35. This is going to be 35 plus 30. This is going to be 30, 25. And then this is going to be 25, 20. And if I put the 1/4 out front, and if I can just factor out, because I think this will help me, a 1/2 from everything, 1/2 times 1, or whatever. Then on the inside, I'm going to get 4 numbers, okay? 40 plus 35, so I'm going to get 75. 35 plus 30, I'm going to get 65. 30 and 25, I'll get 55. And 25 and 20, I'll get 45. And if I add those up, let's see, that's 110, 120, 140, 240, which gives me 30 as a density. So they are the same. Great. Estimate where the trail on the density of hikers is equal to the same average density. Looks like about right there. So, right? The estimate is at time, oh, wait, nope, not time. Miles equals 3. So 3 miles from the trailhead. Write a complete sentence using numbers and units to tell what the integral of this represents. Okay, so here's where we got to be careful. So the integral of this, now not with the 1 over b minus a, this one's just the integral. Remember, integral is like an accumulation of hikers. So between 1 and 5 miles, there are 120, because it was like, guys, it was the before I did the 1/4, you know. No, is that right? It's not 120. What was the integral before I did the 1/4? Yeah, 120. Okay, there are 120 hikers on the trail. Okay. All right, let's go ahead and look at 6, 7, and 8. Here we go. So for number 6, set up but do not integrate an integral which could be used to find the area bounded by these graphs. Now, it would be really helpful if I knew what these look like. That's a parabola that's up 1 and upside down. Okay. Negative x squared plus 1. Okay, this is a parabola that's right side up, minus 3 plus 1, that passes through the points 3 and negative 1. Okay, that's g of x. All right, this is my shaded area right here. Okay, so my area equation is going to be top minus bottom from endpoint to endpoint. Now, the way I find the endpoints is I'm going to go ahead and set these two equal to each other. And it wants me to show the equations that we use. So it wants me to show my work, basically. So x squared minus 2x minus 3 equals negative x squared plus 1. If I add this over, I get 2x squared minus 2x. And if I subtract that over, I get minus 4. If I factor out a 2, and I continue factoring this is x minus 2, x plus 1 is 0. So x equals 2 and negative 1. So that's negative 1, and that's an x coordinate of 2. So then that goes from negative 1 to 2. Okay? Set up but do not integrate. All right, perfect. That's it. Okay. For number 7, let's sketch my region. Okay, you guys all should know, hopefully, what square root of x looks like. Minus 2 on the inside moves it to the right 2. So that's square root of x minus 2. X equals 6 is a vertical line. And then y equals 0, and wants to find the area of that region. And this one wants me to actually do it, not just like set it up, but actually do it. Okay, so we have the integral of the top curve minus the bottom curve, which is just 0, so I don't really need to put that there. Left to right. Now this starts at 2 and it goes up to 6. Okay? Okay, so you guys, this is like u to the 1/2. So when I integrate it, it's going to be u to the 3/2, 2/3. All right. And 6 minus 2 is 4 to the 3/2, and 2 minus 2 is 0 to the 3/2. So this gives me 4 to the 3/2 is the square root of 4, which is 2 to the 3rd, which is 8. So that gives me 16/3 minus 0/3. Okay, so that one just gives me 16/3. All right, perfect. Now, using problem 7 as the base, Find the volume of the solid used by square cross sections perpendicular to the x-axis. Okay, well, my cross section right here, the base of that square is the square root of x minus 2. So for number 8, it's going to be the integral of the area. Now, the area of a square is side squared. And I'm going from 2 to 6. Okay? Cool, perfect. All right, and then let's look at number 9, which is also a set up but do not integrate. The integrals will be used to find the volume following. Problem 7 around the x-axis. So check it out, guys. That's here around the x-axis. So that's just pi r squared. So it's still the integral from 2 to 6. It's pi, and then it's the radius squared. All right? And the radius is just this, square root of x minus 2. All right, and then 9 part B is going to be pi from 2 to 6, and it's going to be outer radius squared minus inner radius squared. And I'm revolving it around the line y equals 4. Okay? Now, if you guys look at this, my outer radius from there to there is just 4. All right? My inner radius is 4 minus whatever that was. So it's my inner radius is 4 minus the square root of x minus 2. Whoops, and I forgot something. Did you guys notice what I forgot? Squared. Both of those are squared. Okay? So cool, that's about a half an hour. So let's call this part 1 of the video, and we'll start part 2 on number 10. And we'll roll through the rest of these.